Okay, so this is homework 10, problem 1. And so we're given a Poisson process where this random variable n of t1 of t2 is lambda is the random variable lambda with respect to t. And so that we're given this, and we should also note that t is equal to t2 minus t1. And so for any given interval where t2 is t1, that is going to give us a different random variable. Let's say it will be respectively n of t1 and of t2. And then we have another time span, let's say t3 or t4, gives us the random variable of t3 and t4. And since we see that these two lines here, they're not overlapping, therefore the random variables at those respective time frames are also independent. And as you can see from this graph here, different time frames result in a different amount of, like, let's say hypothetically k, where k could be like number of earthquakes within that time span. That will also be a different value every time. And so that results in this independent incremental process here. And so in the first part, we are asked to find the expected value of x of t. And if you go back and think about what the expected value of a Poisson distribution before, you would remember that the expected value of Poisson distribution is simply just the random variable lambda. But now this is a Poisson process with respect to time. It's not going to be just lambda anymore because there's also a factor of time. But using our intuition, we can predict that the expected value of x of t is just going to be lambda, but with respect to time, so lambda t. And as you can see in the future, we can prove that. And so we want to put it in this format: k e to the negative lambda t times lambda t k divided by k factorial. Because it's just k times the function, just like the expected value is just x f of x, or summation. Okay, so we want to get into this form. And so we're given this, and so we start with that. So we know that the summation of all probabilities from 0 to infinity is going to be equal to 1. And so we just move e to the negative lambda t over to the other side. And so we get lambda t times k is e over k factorial is equal to e to the lambda t. And so now we want to take the integral of this. And we do the integral with respect to lambda t. Just like how before we did integral with just respect to lambda. But now this is a Poisson process, so it's in respect to t. And not integral, derivative, my bad. But the derivative just gives us k to the lambda t is equal to k minus 1 divided by k factorial is equal to e to the lambda t. Not lambda e to the lambda t, because lambda t here is just a random variable. So it's because we're also doing the the derivative with respect to lambda t. And so we notice that there's an extra lambda t here on this side, which we want to move to the other side. And so since it's lambda t to the negative 1, we just multiply it over to the other side. We get lambda t e to the lambda t. And in order to get it back into this format, we want e to the negative lambda t here on the other side. We just divide that over. And so as we can see before, we get to our expected value u is equal to lambda t. In the second part, in the second part, we were asked to find the autocorrelation of T1 and T2. But as you can see, T2 doesn't always have to be greater than T1. T2 could actually be less than T1. But we're going to do the case where T2 is in fact greater or equal to T1. And so the autocorrelation of T1 and T2 is equal to just this formula, expected value of x of T1 times x of T2. And we can expand that in order to solve, because there are discrete points here at both T1 and T2 where we have to find T1 and then T2 minus T1 and then at T2 to get the autocorrelation. And so we can split it up like this, where we have x of T1 times x of T2 minus x of T1 plus x of T1. And as you can see here, that when we evaluate them all out, these two cancel with each other. We just see what we started with. But going on from this, we can expand this out to the expected value of e to the T1 times the expected value of x of T2 minus T1 times the x of t1s combined, and so we get expected value of x of t1 squared. And so we know all of this except for what the expected value of, except for the second moment of t1, or x of t1. We know what the first moment is. It's just simply equal to lambda t. And so in order to find the second moment, it has to be in the format of k squared e to the negative lambda t times lambda t k divided by k factorial. And so it's just simply just this what we have here, and we do another derivative in order to get the second moment, because the second moment is just the derivative of the first moment. So this is what we have before, and we do the derivative with respect to lambda t again, and so we get k squared is equal to lambda t times k to the negative 1 minus 1 divided by k factorial, and it's equal to the chain rule here, so it's lambda t times e to lambda t, which gives us e to lambda t, plus this times the derivative of this, which this goes equal to 1, so we just get e to the lambda t. And then we notice we have an actual lambda t on this side, so we multiply that across to the other side, and we get lambda t times e to the lambda t times lambda t plus 1. And then we want to move this e to the lambda t back to the other side. And so the second moment is equal to lambda t times lambda t plus 1. So in order for us to find the autocorrelation, we put it back into this formula, and we just put what we found for the second moment into this side, which is lambda t1, because there's respect to t1 this time, not just t. So lambda t1 times lambda t1 plus 1. The expected value of x of t1 is equal to just simply lambda t1, and the expected value of x of t2 is equal to lambda t2 minus expected value of t1, lambda t1. And so we expand this out, we get lambda squared t1 t2 minus lambda squared t2, or lambda squared t1 squared, plus, when we do this, we do lambda squared t1 squared, so we know this middle component cancels out, and then plus lambda t1. And so when this cancels out, we get this, and we notice we can factor out a t1 and a lambda. So it's lambda t1 times lambda t2 plus 1. It's also important to note that since t2 is in fact greater than t1, t1 can be rewritten as lambda of the minimum of t1 and t2. And the minimum of t1 and t2 become important in the future, so we should write it in this way. Times lambda t2 plus 1. Similarly, if t1 was in fact greater than t2, these would just all be switched. However, min still stay the same because this still gives us t2 at the end. But t2 becomes t1 when it's the autocorrelation of t2 t1 if t1 is in fact greater than t2.